Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 8, 2026, just yesterday. It introduces a geometric framework for off-chain payment systems like the Lightning Network, proving that multi-party channels are significantly more capital efficient than standard two-party connections. The paper is titled, A Mathematical Theory of Payment Channel Networks. And as we'll see later, the insights into channel depletion offer some really promising ways to make these networks sustainable at scale. To start, Figure 1 visualizes the core concepts using a concrete example. The top panel defines a simple network with three nodes, A, B, and C, connected by payment channels with fixed capacities. To the right, the grid plot maps out the liquidity polytope LG, where each dot represents a mathematically valid distribution of coins across these channels. Below in panel B, we see the resulting liquidity network for one specific state, indicating the directional capacity available on each link, which determines the maximum payable amounts shown in the table. Well, Figure 2 quantifies the size of this state space by plotting the volume of the liquidity polytope, which represents the number of feasible states, against the channel count on the horizontal axis. The colored curves correspond to different total coin amounts, showing a clear peak for each supply level. The black dashed line traces these maxima, indicating an optimal channel density. This implies that for a given amount of capital, there is an ideal way to partition it. Fragmenting coins too much or consolidating them too heavily reduces the overall number of possible liquidity configurations. So, while Figure 2 looked at the raw count of liquidity states, Figure 4 now shifts to the resulting wealth distributions. This triangular grid maps every way to divide 21 coins among three participants, with axes for Alice, Bob, and Carol. The scattered blue dots show states that are valid on-chain, but unreachable in the payment network. In contrast, the solid red cluster highlights the subset that is actually feasible within the channels. Notice that the red region covers only about 52% of the space, visually demonstrating how channel capacities constrain the network's reachable financial states. Alright, moving from theoretical constraints to practical performance, Figure 7 shows how these limits impact speed. The chart plot supported payment bandwidth on the vertical axis against the transaction amount on the horizontal axis. You can see two colored curves representing different channel configurations, but they both tell the same story. The steep downward trend reveals a critical bottleneck. The network handles tiny payments efficiently, but throughput collapses as payment size grows. This occurs because larger transfers are statistically more likely to fail off-chain, forcing the system to rely on slow on-chain settlements. Okay, Figure 9 investigates the structural root of these limitations. It plots the observed number of depleted channels on the vertical axis against the network circuit rank on the horizontal axis. The circuit rank serves as a measure of topological complexity, counting the independent loops in the graph. The scatter plot reveals a perfect linear correlation with a slope of 1. This confirms the theory that rational fee maximizing behavior drives the network to a boundary state, where one channel depletes for every cycle, effectively collapsing the active structure into a tree. So, seeing that networks tend to deplete, Figure 11 demonstrates how changing the fee structure fixes this. These three panels track liquidity levels on different channels over thousands of payment steps. Under the standard linear fee model, shown by the blue and orange lines, the balance rapidly hits zero, or the maximum capacity, effectively killing the channel's utility. However, the green and red lines represent the proposed convex fee schedule. In this case, the liquidity naturally stays centered around 500, proving that dynamic pricing can act as a stable flow control mechanism. Well, having seen how fees stabilize the network, this table breaks down the arithmetic of a single payment circulation. The first column tracks a variable t, representing the transfer magnitude. The middle columns show how this flow shifts the balances on channels EX, FY, and GX relative to the capacity limits in the headers. The green rows highlight the feasible range, where t is between 0 and 3. In contrast, the red rows mark failure points. Specifically, at t equals 4, the first channel overflows, rendering the transaction infeasible. Wrapping up, two big takeaways stand out. First, standard two-party channels face a mathematical ceiling, where efficiency naturally collapses into depletion. Second, the path forward likely involves adopting multi-party channels and convex fee structures to actively maintain liquidity. It forces us to rethink the fundamental geometry of off-chain scaling. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.